Executing a direct HTTP callout from an Apex trigger is architecturally prohibited by the core infrastructure of the Salesforce platform. If you attempt to force this connection, the system immediately halts the transaction and throws a fatal system.callout exception. This restriction presents a challenge when a record insertion must trigger an immediate notification to an external REST API. While business logic often requires external synchronization, Salesforce's infrastructure explicitly prevents a direct bridge within the trigger. This is due to the synchronous execution context of the database trigger lifecycle, which requires all logic to complete in a single continuous operation. Network I/O introduces an inherently unpredictable variable into this high-speed environment. Internal database operations execute in microseconds, while external HTTP requests rely on variable internet latency and remote server response times. We will deconstruct the mechanics of this synchronous bottleneck and evaluate the two supported asynchronous frameworks to determine the enterprise standard. Salesforce enforces this strict separation to protect the multi-tenant database from blocking integrations that could stall shared processing resources. This diagram maps the timeline of a database transaction. The moment a new record is inserted, a single execution thread begins. The transaction acquires an exclusive lock on that record to maintain absolute data integrity during the operation. In a prohibited state, an HTTP request would fire directly from within this locked synchronous thread. While the external server processes the payload, the original timeline thread remains paused, holding its lock on the database row. Other system transactions requiring access to that row begin to pile up, creating immediate resource starvation. The thread eventually hits the platform's hard timeout limits, causing the primary transaction and all pending operations to fail. To prevent this, the network request must be decoupled from the database transaction lifecycle. Salesforce provides specific asynchronous contexts engineered to execute this decoupling safely. Asynchronous decoupling is fundamentally the only mathematically viable way to execute network I/O without degrading core database integrity. The simplest syntactical method to offload a process from the main thread is the @future annotation. For external integrations, developers must explicitly declare callout equals true to grant the method network access. This mechanism extracts the payload and drops a message into an isolated system queue. Once the message is queued, the original database transaction immediately closes and releases its lock. A separate background thread picks up the message and executes the HTTP callout independently. This provides a straightforward solution for basic data transmission requirements. However, this fire and forget mechanism has significant operational limitations. @future methods only accept primitive data types, such as sets of IDs, and cannot process complex S-objects. These static methods also lack the structure needed to orchestrate sequential tasks or track their own internal state. While it resolves the transaction lock, the lack of state management makes the @future approach brittle for mission-critical enterprise integrations. For complex integration control, enterprise architects utilize queuable Apex. Custom classes implementing the queuable interface provide the structure for these jobs. Executing network requests in this context requires the implementation of a secondary interface, database.allows callouts. Queuable Apex uses instantiated, stateful class objects rather than the isolated static methods used in @future calls. Encapsulating the job as an object determines how system memory and variable state are managed during execution. The trigger uses the system.enqueueJob method to dispatch the instantiated class into the queue. This diagram illustrates how stateful objects enable execution chaining. Chaining allows complex, sequential API workflows to be orchestrated, where each process guarantees the start of the next. The object-oriented nature of queuable also facilitates granular retry logic. The object can catch a network timeout, preserve its payload, and deliberately re-queue itself for a subsequent attempt. Encapsulating the callout within a queuable object creates a resilient, self-managing system component. To maintain platform stability, synchronous execution contexts must remain separate from unpredictable network I/O. Choosing between @future and queuable involves a trade-off between syntactical simplicity and operational control. This matrix evaluates both approaches against production-grade requirements. The @future approach lacks support for complex state, sequential chaining, and self-directed retries. Queuable Apex provides the architecture required for all three advanced enterprise requirements. The @future annotation is still appropriate for trivial, non-critical tasks like basic logging. However, fire and forget logic is insufficient for critical financial syncing or operational data integrations. Queuable Apex should be the standard for production-grade external callouts in any professional environment. System reliability is achieved by architecting integration patterns that actively manage and recover from network failure.